Good morning. Today we're going to explore one of the most extraordinary climatic events in recorded history, the year without a summer. In 1816, across the northern hemisphere, summer simply never arrived. Snow fell in June, lakes froze in July, and crops withered under relentless frost. What makes this event so compelling is not just its dramatic effects, but its cause, a volcanic eruption on the other side of the world, in what is now Indonesia. We'll trace how the Tambora eruption of 1815 triggered a global cascade of climate disruption that changed the course of history. This is a story about how our planet's climate system connects events thousands of miles apart in ways that were barely understood at the time. Let me outline our journey through this topic. We'll begin by examining what actually happened in 1816, the first-hand accounts, the frozen landscapes, the failed harvests. Then we'll travel back to the source, the Mount Tambora eruption of April 1815, a supercolossal event unlike anything in modern experience. From there, we'll look at the global temperature data, the human toll, the scientific mechanism of volcanic winter, and finally, the broader context of other contributing factors. By the end, I hope you'll see why this event remains so significant for climate science today. Nearly 2 centuries later, it continues to inform how we model and understand climate perturbations. Let's begin by immersing ourselves in what the world experienced in 1816. Imagine waking up in June to find your fields buried in snow. Not a light dusting, but heavy, crop-killing snow. In New England, people called it 1800 and froze to death, and the summer of mittens. These weren't poetic exaggerations. They were desperate attempts to name something unprecedented. Across the northern hemisphere, from the eastern United States to western Europe, the summer of 1816 simply never arrived. The eyewitness accounts paint a picture that's almost surreal in its bleakness, a world where the seasons had come undone. Look at the scale of what happened across the eastern United States. In New England, frost was recorded in every single month of 1816, not just a late spring frost, but frost in June, July, and August. In Albany, New York, and Dennisville, Maine, heavy snow blanketed the ground in June, the month when crops should have been growing vigorously. In July, normally the hottest month of the year, lakes and rivers remained frozen as far south as northwestern Pennsylvania. Cape May, New Jersey endured 5 consecutive nights of frost, and even in Virginia, frost persisted into late August, deep into what should have been harvest season. Perhaps most striking of all, temperatures could swing from above normal summer heat to near freezing within just a few hours. As one contemporary account put it, it was as if the climate had simply gone mad. Before we examine the cause, let me put some numbers on the scale of what we're dealing with. The Tambora eruption registered a volcanic explosivity index of 7. That's classified as supercolossal. To put that in perspective, the 1980 Mount St. Helens eruption was a VEI 5, and the scale is logarithmic. Each step represents a 10-fold increase in ejecta volume. Tambora ejected at least 37 cubic kilometers of dense rock equivalent material into the atmosphere. The resulting temperature anomalies were staggering. Iceland experienced a cooling of 1.33 degrees Celsius below the norm, the largest anomaly recorded. And this was not a localized event. All 31 islands analyzed in one comprehensive study showed negative temperature anomalies in 1916. The fingerprint unmistakably global. So what could possibly cause the entire northern hemisphere to freeze in summer? The answer lies on a small island in the Indonesian archipelago called Sumbawa, home to Mount Tambora. In April of 1815, this volcano unleashed the largest eruption in recorded human history, a supercolossal event that would reshape the global climate for years to come. The connection between a tropical volcano and frozen New England fields may seem improbable, but the science is remarkably clear. Let's examine exactly what happened when Tambora erupted. Mount Tambora erupted in April 1815 with a force that dwarfs anything in modern memory. It remains the most recent confirmed VEI 7 eruption, the largest in recorded history and one of the 2 largest eruptions in the past 2,000 years. The eruption column injected vast quantities of sulfur dioxide directly into the stratosphere, where it underwent chemical conversion to sulfate aerosols. These microscopic particles, far smaller than the width of a human hair, spread around the globe within weeks to months, forming a reflective veil that reduced the sunlight reaching Earth's surface. Because these aerosols were suspended in the stratosphere above the weather systems that would normally wash them out, they persisted for well over a year. And the climate effects began almost immediately. Cooling was detectable by the summer of 1815, just months after the April eruption. The world was already feeling Tambora's impact before anyone could have connected cause and effect. Let's walk through the chronology of this climate disruption. The eruption reached its violent climax on April 10, 1815, on Sumbawa Island in what is now Indonesia. Within months, by the summer of 1815, initial cooling was already being detected in the northern hemisphere. The aerosol veil was spreading and beginning its work. Curiously, the winter of 1815 to 1816 was actually slightly milder than average, which may have masked the impending crisis and left communities dangerously unprepared for what was coming. Then came spring 1816. Persistent cold set in with a vengeance, and May frosts killed off most crops across New York, Massachusetts, New Hampshire, and Vermont. By summer 1816, the crisis reached its terrifying peak. Snow in June, frozen lakes in July, and what should have been harvest season transformed into a frozen nightmare. Cooler than normal patterns persisted stubbornly into the spring of 1817 before the climate system gradually recovered nearly 2 full years after the initial eruption. This chart shows the temperature anomalies recorded across several islands and regions in 1816, drawn from a comprehensive analysis of 31 island temperature records. The data is striking in both its magnitude and its consistency. Iceland experienced the most severe cooling, at negative 1.33 degrees Celsius, below the climatic norm. Great Britain followed at negative 1.12 degrees. Even as far away as Honshu, Japan, the anomaly reached nearly negative 1 full degree, almost minus 0.91. And critically, even Marajo, an island at the mouth of the Amazon in the tropics, showed a negative anomaly, albeit very small, at just negative 0.01 degrees. Every single one of the 31 islands studied showed cooling without exception. This is the unmistakable fingerprint of a global climate-forcing event. No region was entirely spared, even if the severity varied dramatically by latitude and geography. The human cost of this climate catastrophe was devastating. Historian John D. Post described 1816 as the last great subsistence crisis in the Western world. And that phrase, subsistence crisis, captures the existential nature of what communities faced. Across New England, trees remained leafless and brown throughout the entire year. Oak trees failed to grow entirely, leaving a missing growth ring for 1816 that dendrochronologists still use today to identify the event in tree ring records. Small migratory birds died in massive numbers. Their bodies littered the frozen fields because the insect populations they depended on had collapsed. Crop failures triggered severe food shortages, and food shortages in turn triggered unrest. In Europe, the situation was equally dire. The cold, wet conditions led to widespread harvest failures that compounded the economic distress following the Napoleonic Wars. This was far more than a meteorological curiosity. It was a genuine humanitarian crisis that reshaped communities on both sides of the Atlantic. Let's examine the mechanism more closely, because it reveals something profound about how our planet's climate system works. On the left, we see the volcanic winter process. Sulfate aerosols injected into the stratosphere spread globally within weeks to months. These particles are remarkably effective at reflecting incoming solar radiation. They act like a giant, invisible mirror suspended in the upper atmosphere. Because they're in the stratosphere, above the turbulent weather systems of the troposphere, they are not washed out by rain and can persist for 1 to 3 years. This creates a sustained cooling effect that disrupts the normal seasonal temperature cycle, particularly in the mid-latitudes of the northern hemisphere. On the right, we see what people actually observed at ground level: a persistent dry fog and a sulfurous haze that hung in the sky for months. Sunsets turned spectacularly vivid. Those lurid reddish and orange skies, captured in the paintings of J.M.W. Turner from this period, are now understood to be a direct artistic record of stratospheric aerosol scattering. The optical phenomena confirmed what the thermometers were showing. The atmosphere had been fundamentally altered by an event on the other side of the world. While Tambora was unquestionably the dominant cause of the year without a summer, it may not have been acting entirely alone. The period from roughly 1790 to 1830 coincided with what solar physicists call the Dalton minimum, a period of reduced solar activity that may have contributed a subtle background cooling, though its magnitude was far smaller than the volcanic signal. Several other volcanoes also erupted at VEI 4 or greater around this time, including significant eruptions in 1808, 1812, and 1814. These events may have primed the atmosphere with residual aerosols, creating conditions in which Tambora's impact was amplified. However, the scientific consensus is unequivocal. Tambora's VEI 7 eruption was the overwhelming driver of the 1816 climate anomaly. And this is where the story connects to our present moment. Modern climate models use the year without a summer as a critical validation case. If you can successfully model Tambora's effects, you build confidence in your model's ability to simulate other climate perturbations, both natural and anthropogenic. This event, now more than 2 centuries old, continues to sharpen our understanding of the Earth's climate system and its profound interconnectedness. Now let's turn to something extraordinary: the cultural ripples of this climate disaster. In the summer of 1816, a group of writers gathered at Villa Diodati on Lake Geneva: Mary Shelley, Percy Shelley, Lord Byron, and John Polidori. Trapped indoors by relentless rain and cold, Byron challenged each guest to write a ghost story. From that challenge, Mary Shelley, just 18 years old, conceived Frankenstein, a novel that would birth modern science fiction. Byron himself wrote Darkness, a poem so bleak it envisions the literal death of the sun. And Polidori's The Vampire launched the vampire genre that stretches to our own day. Meanwhile, back on the ground, the practical consequences were unfolding. Carl Dreiss, watching horses starve for want of oats, invented a human-powered two-wheeled vehicle, the ancestor of the bicycle. In the art world, the strange orange and crimson sunsets of 1816 are thought to have influenced J.M.W. Turner's later atmospheric masterpieces. And across New England, thousands of farming families simply gave up and moved west, accelerating the settlement of the American frontier. A single volcano on the other side of the world didn't just freeze crops, it reshaped literature, art, technology, and demography. So what does the year without a summer teach us 2 centuries later? First, it reminds us that natural climate forcings can be sudden, severe, and global in reach. Tambora was not the product of industry or human activity. It was a geological event that nonetheless produced a humanitarian catastrophe across continents. Second, it exposes the fragility of agricultural systems to even modest temperature drops. A cooling of 1 to 1.5 degrees Celsius was enough to cause the last great subsistence crisis in the Western world. Today, as we debate geoengineering proposals that would deliberately inject aerosols into the stratosphere to cool the planet, 1816 stands as both a natural experiment and a cautionary tale. We have already seen, in real history, what happens when the sun is dimmed. Third and finally, the year without a summer reminds us that climate is not merely a backdrop to human affairs, it is a protagonist. It shapes what we eat, where we live, what we create, and how we imagine the future. The cold summer of 1816 gave us Frankenstein, the bicycle, and a lasting scientific puzzle, and it left scars on the historical record that we are still reading today. Thank you.